Research and development in semiconductor equipment manufacturing. Research and development in semiconductor equipment manufacturing is the engine that powers innovation across the entire electronics industry. It focuses on pushing the boundaries of what's possible in lithography, deposition, etching, and inspection technologies, four critical areas that define the capabilities of chip production. As we look ahead, the sector is experiencing a surge in investment and innovation. In 2024, the global equipment market reached a value of $117 billion, highlighting its immense scale and importance. Notably, 19.5% of revenue is being reinvested into R&D, showcasing the industry's commitment to continual advancement. Companies are racing to meet the growing demand for 3-nanometer and smaller node technologies, which are foundational to next-generation devices. This evolution shapes the performance, efficiency, and miniaturization of electronics, supporting applications from AI and mobile to cloud computing and automotive systems.
Industry overview. The semiconductor equipment industry reached $117 billion in global sales for 2024, reflecting a strong 10% year-over-year growth rate. This upward momentum highlights increasing demand for advanced chips across sectors like AI, automotive, and mobile computing. The Asia-Pacific region dominates the market, accounting for 75% of equipment demand, followed by North America at 15% and Europe at 10%. Key equipment categories include lithography at $25 billion, deposition at $22 billion, etching at $18 billion, and inspection at $15 billion. Additional categories such as ion implantation and CMP equipment also contribute significantly. Market leadership is held by ASML in lithography, Applied Materials across multiple segments, Tokyo Electron in etching and deposition, and Lam Research in etching. Looking ahead, the growth forecast shows a continued rise, projecting the market to surpass $130 billion by 2026. These trends reflect sustained global investment in next-generation semiconductor manufacturing capabilities. Key manufacturing technologies. Semiconductor manufacturing depends on several core process technologies, each playing a crucial role in device fabrication. Lithography is a pattern transfer process, using EUV technology at 13.5 nanometers to achieve resolution limits below 3 nanometers, with a market share of 21%. Etching, a material removal process, is dominated by plasma etching, used in 90% of applications, with selectivity ratios reaching 100.1 and a total market value of $18 billion. Deposition technologies, such as atomic layer deposition, ALD, and chemical vapor deposition, CVD, enable atomic-level thin film creation, serving over 15 methods and contributing to a $22 billion market. Ion implantation provides precise doping with energy ranges from 1 to 200 keV nanometers and an accuracy of plus or minus 1%, totaling $8 billion in value. Chemical mechanical planarization, CMP, ensures surface uniformity within plus or minus 2 nanometers, with removal rates between 100 to 500 angstroms per min and a $6 billion market. Lastly, inspection systems detect defects down to 1 nanometer, with 200 wafers per hour throughput, supporting a $15 billion industry. Key manufacturing technologies, technology innovation drivers. Several innovation drivers are accelerating progress in semiconductor manufacturing and reshaping how chips are designed and produced. First, Moore's law continues to guide the industry's effort toward transistor scaling, where device sizes are continually reduced while increasing performance and maintaining cost efficiency. This principle underpins much of the industry's roadmap. Second, artificial intelligence and machine learning are becoming essential for process optimization. AI/ML is applied to monitor data, detect anomalies, and improve yield and efficiency across the fabrication process. Third, 3D NAND represents a shift toward vertical scaling, stacking memory layers to increase density without shrinking features horizontally, enabling greater storage in smaller spaces. Lastly, extreme ultraviolet lithography, or EUV, is a game-changing next-generation lithography technology. It allows chip makers to print patterns at extremely small scales using 13.5 nanometer wavelength light, supporting advanced nodes below 3 nanometers. Together, these drivers fuel critical manufacturing capabilities for next-generation semiconductor devices. R&D investment trends. Research and development is the lifeblood of innovation in the semiconductor industry. In 2023, the U.S. semiconductor sector invested $47.4 billion in global R&D efforts, marking a 9.8% year-over-year increase. This commitment highlights how central innovation is to maintaining competitiveness and driving progress in chip technology. R&D intensity, measured as a percentage of revenue, stands at 19.5%, ranking second only to the biotechnology sector. This high intensity underscores how much the semiconductor industry reinvests into future development. Equipment R&D specifically accounts for $12.8 billion of annual spending, representing 27% of the industry's total R&D investment. This allocation emphasizes the critical role of advanced tools in enabling cutting-edge manufacturing. Additionally, the industry filed 24,500 patents annually, reflecting a 12% year-over-year growth in intellectual property activity. These trends demonstrate that the semiconductor sector is not only high-tech, but also highly dynamic, driven by constant innovation and intellectual leadership. R&D investment trends. Global R&D investment is shaping the future of the semiconductor industry through strategic geographic distribution and evolving priorities. Regionally, Asia-Pacific leads in spending, investing $18.5 billion, which accounts for 39% of global R&D. North America follows closely with $16.2 billion or 34%, while Europe contributes $12.7 billion, making up 27%. This regional split reflects global hubs of innovation and manufacturing strength. On the priority front, EUV lithography commands the highest focus, representing 32% of investments due to its critical role in next-generation chip fabrication. AI and machine learning integration follows at 24%, supporting smarter process control and automation. Advanced etching garners 18%, emphasizing precision in pattern transfer. 3D NAND technology receives 15%, reflecting memory scaling efforts, while sustainability, at 11%, signals growing attention to environmental responsibility. Key emerging R&D areas include AI-driven manufacturing at 3.2B, automation at 2.5B, 3D integration at 2.1B, green tech at 1.8B, and cybersecurity at 1.2B. Major technology challenges. Semiconductor innovation is advancing rapidly, yet key technological hurdles remain. One critical challenge is EUV complexity, especially in manufacturing precision. EUV lithography uses a 13.5 nanometer wavelength, allowing for ultra-fine patterning necessary for next-gen chips. However, the systems require an intense 250-watt power source, creating significant technical barriers. These include issues with optics, resist materials, and mask defects. To overcome these hurdles, the industry is investing heavily in high-NA EUV systems, which offer better resolution but bring even greater engineering demands. Another high-priority challenge is advanced materials. As integration challenges grow, the industry needs to discover and implement over 5 new materials to meet evolving performance and scaling requirements. Despite $2.8 billion already invested in R&D, the path forward remains complex due to compatibility issues, yield concerns, and long development cycles. AI-assisted material discovery is emerging as a promising approach to accelerate breakthroughs in this high-complexity area. Major technology challenges. The semiconductor industry faces several urgent and high-impact challenges that shape innovation strategy and investment. One major hurdle is process control, where atomic-level precision is essential. Achieving a tolerance of plus or minus 0.5 nanometers with 99.9% uniformity demands advanced monitoring and feedback systems. Machine learning-based process control is emerging as a key solution to address variability and improve outcomes. cost scaling presents a critical economic challenge. Building a new fab can exceed $20 billion, and equipment costs increase by 25% with each new node. These escalating costs threaten economic viability. Chiplet architecture is being explored to help manage complexity and reduce expenses. Sustainability is also a pressing concern, with the semiconductor industry accounting for 3% of global energy use and high water consumption. Green manufacturing techniques are vital to reducing environmental impact. Supporting data shows that 87% of companies are facing critical challenges, with $155 billion in annual equipment investment. Complexity causes delays in 42% of projects. AI and ML are central to most solutions, but implementation can take 5 to 7 years. Next-generation technologies will be required to meet future demands. Innovative R&D solutions. To tackle the industry's most pressing challenges, several innovative R&D solutions are being actively developed and deployed. One major breakthrough is high-NA EUV, the next generation of extreme ultraviolet lithography. With a resolution capability of 8 nanometers and a productivity increase of 40%, this technology is currently in the pilot phase, driven by the development of 0.55 numerical aperture optics. High-NA EUV is essential for continued scaling in advanced nodes. Quantum computing is another frontier, especially valuable in material simulation. It offers a massive 1000x speedup in simulation tasks and has attracted $890 million in R&D investment. While still in the early stages of maturity, quantum computing promises to revolutionize how we discover and validate materials. In parallel, digital twin technology is gaining ground with $1.5 billion invested in virtual simulations that help model and optimize fab operations. 3D packaging using chiplet integration delivers up to 80% cost reduction. Green tech innovations enable a 35% reduction in fab energy use, supporting sustainability goals. Lastly, automation powered by smart robotics is achieving 99.8% precision, enhancing both yield and efficiency across semiconductor manufacturing lines. Innovative R&D solutions. Breakthrough technologies are reshaping semiconductor manufacturing timelines and outcomes. The innovation timeline highlights 3 key waves of progress. From 2024 to 2025, AI solutions are being implemented, driving early gains in efficiency. Between 2025 and 2027, high-NA EUV lithography is projected to become mainstream, pushing resolution and productivity further. From 2027 to 2030, quantum applications are expected to mature, unlocking powerful capabilities in material simulation and system modeling. These innovations are already having measurable impact. Manufacturing efficiency has improved by 22% through the integration of AI and automation, leading to faster, smarter production lines. Defect reduction has been dramatic, with machine learning-based process control cutting defects by 67%, which improves yield and device reliability. Finally, development speed has increased 3.5 times, thanks to the combined use of digital twins and quantum computing. These technologies enable rapid prototyping and predictive simulations, significantly accelerating R&D cycles and time to market for new chip designs. Global R&D ecosystem. The global R&D ecosystem in semiconductor manufacturing is powered by collaboration among industry leaders, academic institutions, and government agencies. ASML leads in EUV lithography from Europe with an R&D spend of $3.2 billion and an impressive 95% market share. In the USA, Applied Materials dominates deposition and etching, investing $2.8 billion in R&D and achieving 85% global reach. From Asia, Tokyo Electron stands out in process equipment, with $195 billion in R&D investment and a 78% innovation index. These companies form the core of a collaborative innovation network. The ecosystem spans a global network involving MIT for materials, TSMC for process technologies, and IMEC for nanotech innovations. Key metrics include over 450 industry-academia partnerships, $28 billion in government funding through national initiatives, and an 85% success rate in cross-border R&D projects. This ecosystem drives next-generation advancements through shared knowledge and coordinated global efforts. Global R&D ecosystem. The global R&D ecosystem in semiconductor equipment innovation is regionally distributed and strategically concentrated in several high-impact innovation hubs. The Asia-Pacific region leads R&D distribution with 45% of global activity, driven largely by countries like Taiwan and Korea. North America follows with 35%, powered by innovation centers such as Silicon Valley. Europe contributes 20%, with a strong focus on specialized fields like lithography, particularly in the Netherlands. These regions form the backbone of a highly collaborative, cross-border innovation network. Key innovation hubs include Silicon Valley, which functions as the headquarters for semiconductor equipment development, the Netherlands, a global leader in lithography technologies, Taiwan, known for advanced fab innovation, and Korea, which excels in memory technology. Supporting this global effort are 85,000 R&D personnel and a total annual investment of $47 billion, driving breakthroughs through continuous collaboration and concentrated technological expertise. Future outlook. The future of the semiconductor equipment market is defined by rapid expansion and groundbreaking technological advancements from 2025 to 2035. The global equipment market is expected to grow from $135 billion in 2025 to $280 billion by 2030, eventually reaching $520 billion by 2035. This translates to a strong compound annual growth rate of 15.2%, signaling sustained demand for advanced semiconductor manufacturing technologies. On the technology roadmap, the years 2025 to 2027 will see the mass production of 3 nanometer nodes and active research into 2 nanometer nodes, representing the next frontier of scaling. Between 2027 and 2030, the focus shifts to quantum integration, where AI-enhanced manufacturing will transform process efficiency and chip performance. Looking further ahead to 2030 to 2035, molecular assembly will emerge, enabling atomic-scale precision and ushering in an era of ultra-miniaturized, highly efficient semiconductor devices. This outlook reflects a decade of aggressive innovation and exponential growth. Future outlook. From 2025 to 2035, the semiconductor industry is set to undergo transformative changes through AI, quantum computing, and green technology. The AI revolution, taking place between 2025 and 2027, will drive autonomous manufacturing. With a market impact projected at $45 billion, AI systems will increasingly manage equipment, optimize workflows, and improve yields with minimal human intervention. Although adoption is still growing, the shift toward automation is accelerating. Between 2027 and 2030, quantum computing will advance process optimization, enabling unprecedented computation speeds and real-time modeling of complex materials. With $12 billion already invested, readiness is progressing, although widespread implementation will take time. Concurrently, green technologies will support carbon-neutral fabs from 2025 through 2028. These initiatives are expected to yield up to 60% in energy savings, contributing to both environmental sustainability and cost efficiency. Implementation is well underway, positioning the industry for a greener, smarter, and more efficient future. Future outlook. Between 2025 and 2030, the semiconductor industry will prioritize strategic investments to enable groundbreaking advancements. The leading area of investment is AI and automation, capturing 35% of the focus as companies aim to implement intelligent, self-regulating manufacturing systems. Advanced lithography follows at 28%, supporting next-generation nodes and precise patterning essential for smaller, more powerful chips. Quantum technologies are also receiving significant investment, 22%, as the industry prepares for the integration of quantum computing into manufacturing optimization. Sustainability rounds out the list with 15%, driving eco-conscious practices and energy-efficient operations. These investments are expected to deliver transformative breakthroughs. Manufacturing speed is projected to increase tenfold by 2030, drastically accelerating production timelines. Defect rates could be reduced by as much as 95%, approaching near-zero error levels. Additionally, energy efficiency is forecasted to improve by a factor of 5, making semiconductor fabrication significantly more sustainable and cost-effective in the decade ahead. Innovation leadership. A critical factor in achieving long-term competitive advantage is innovation leadership, especially in the area of breakthrough technology development. This leadership is fueled by strong investment in research and development. With 19.5% of revenues allocated to R&D, the organization demonstrates a firm commitment to discovering and commercializing new technologies. This investment leads to a high success rate of 92%, which signifies that most development efforts translate into market-ready solutions. Being first to market allows the company to set industry standards and command premium pricing, making innovation not just a differentiator, but a strategic asset. This success is not accidental. It's the result of systematic development processes, cross-functional collaboration, and an environment that fosters creative problem-solving. The innovation pipeline is structured to accelerate technology adoption and reinforce the company's position as a global technology leader. Talent excellence. Talent excellence is another critical driver of performance and innovation. The strength of the organization's workforce is reflected in its high density of expertise, 125 PhDs per 1,000 employees. This statistic highlights a deep reservoir of world-class knowledge across disciplines. Such expertise is essential for solving complex technical problems, driving innovation, and maintaining operational excellence. Equally important is the ability to retain top talent. An impressive retention rate of 88% suggests that the organization fosters a strong culture of engagement, continuous learning, and career development. Keeping talent not only maintains intellectual capital, but also strengthens institutional memory and cross-functional collaboration. These professionals are at the core of developing differentiated solutions, mentoring the next generation, and contributing to sustained performance. Their presence ensures that the company remains at the forefront of scientific and technical advancements. Global collaboration. Global collaboration plays a high-priority role in driving innovation and competitiveness through strategic partnerships. The organization boasts over 450 partnerships worldwide, demonstrating a robust and extensive network. These partnerships are not just symbolic. They result in significant joint activity, with 75% of collaborations producing active joint projects. This high level of project engagement enhances the company's ability to share knowledge, reduce time to market, and co-develop advanced technologies. Strategic partnerships span across academic institutions, industry consortia, and other key stakeholders, allowing for shared risks and mutual benefits. The ecosystem built through these collaborations supports open innovation and positions the organization within a broader value chain. It also facilitates global market access and resource sharing, while reinforcing thought leadership across multiple technology domains. This collaborative approach ensures that innovation is accelerated, scaled, and sustained over time. Strategic pillars driving R&D excellence. Driving semiconductor equipment, R&D excellence requires a strong foundation in investment, innovation, and execution. With $47 billion allocated annually to R&D, this represents a bold commitment to future technology leadership. The impact of this investment is seen in the 85% project success rate, showing a highly efficient development pipeline. Additionally, 12,500 patents filed each year reflect a culture of innovation and strong intellectual property generation. A 2.5x speed advantage over competitors enhances the company's agility and responsiveness to market needs. Best practices make this performance possible. Cross-functional teams break down silos and encourage collaboration. A fail-fast methodology accelerates learning by quickly identifying and correcting flaws. Customer co-innovation ensures relevance, while technology roadmapping aligns goals with future trends. Digital twins improve modeling and simulation accuracy, and AI/ML integration supports predictive analytics and automation. These practices enable excellence indicators like a top 1% innovation index, a world-class patent portfolio, and industry-leading time to market. Conclusion and next steps. Looking ahead, the semiconductor equipment market is on track for exponential growth, expected to reach $520 billion by 2035. This expansion presents a significant opportunity for organizations that are prepared to lead through innovation and execution. One of the most transformative developments driving this growth is a tenfold increase in manufacturing speed, made possible by advances in AI and automation. These technologies streamline operations, reduce cycle times, and enable real-time optimization. To support this progress, the continued commitment of allocating 19.5% of revenue toward R&D investment ensures a strong foundation for breakthrough innovation. Just as crucial is quality improvement, where a 95% reduction in defects represents a major leap in manufacturing precision and reliability. Together, these pillars, market expansion, speed acceleration, sustained R&D, and defect minimization, form the strategic roadmap for achieving industry leadership and capturing future value. Strategic vision and critical actions. Semiconductor equipment R&D is now entering a phase of unprecedented transformation, driven by technologies like artificial intelligence, quantum computing, and molecular manufacturing. These advancements are not just incremental, they are redefining the future of the industry. To support this evolution, the organization commits $47 billion annually to R&D, achieving an impressive 85% project success rate. This effort results in 12,500 patents filed each year and over 450 active global partnerships, highlighting the scale and momentum of innovation. To maintain this leadership, 5 critical actions must guide the strategic roadmap. First is AI integration, enabling autonomous and adaptive manufacturing systems. Second, forging quantum partnerships will accelerate progress through shared technology development. Third, talent development ensures a next-generation workforce capable of driving future breakthroughs. Fourth, sustainability must remain a core focus, emphasizing carbon-neutral process innovations. And finally, global collaboration will expand the innovation ecosystem and maximize collective impact. The future starts now. The semiconductor equipment industry is entering a transformative decade, and the time to act is now. Future success will depend on building strong strategic partnerships and executing with relentless precision. These two elements, collaboration and flawless delivery, form the backbone of competitive advantage in this rapidly evolving landscape. The companies that begin their R&D journeys today, making decisive moves in innovation, will be the ones that define tomorrow's market leaders. The next 24 months are especially critical. This period represents a window of opportunity where time to market, investment direction, and technology leadership will be set. Initiating the R&D journey now positions organizations to capitalize on exponential growth, technological disruption, and evolving customer needs. Those who wait risk falling behind. In contrast, those who move swiftly and strategically will shape the industry's future, unlock new value, and establish themselves as leaders for the next generation.